Hi everyone. In this lesson I'm going to talk about two things. One of them is a new word, and that's what I've written up here. It's a word called impedance. Now the word to impede means to come in the way, to halt the progress of. That's what impede means. Now in an AC circuit, whenever you have any sort of components in the circuit, what they do is they have what we call a current limiting effect. And so the total current limiting effect of all the components in an AC circuit is called impedance. And the symbol for impedance, the total current limiting effect, is represented by the letter Z. Now, when you're talking about just a resistor in the circuit, the impedance of a resistor is called resistance. And so for a resistor in a circuit, the current limiting effect of a resistor is called resistance, and the symbol for resistance is R, and resistance is measured in ohms. Okay. If you have a capacitor, a pure capacitor in a circuit, the capacitor too has a current limiting effect, and this current limiting effect of a capacitor is another new word. The word is reactance. And the symbol for reactance is the letter X. And we put a little C to say that it's the reactance of a capacitor. And because it's a current limiting effect, this is also measured in ohms. If instead of a capacitor, you just have an inductor in a circuit, in an AC circuit, so all this is for AC circuits. So the impedance of an inductor is also called reactance. So both these words are similar, but just to make it different from the reactance of a capacitor, we put X with the subscript L, and that is also measured in ohms. So impedance is also measured in ohms. So it's just the current limiting effect, but they're just known by different names depending on what the component is in an AC circuit. So when you write answers, when you're talking about the current limiting effect of a capacitor or an inductor, the term that we use is reactance. And if it's just a resistor, we use the word resistance. Now that's the first part of this lesson. The next part of this lesson is to do with what happens if there is a capacitor in a pure AC circuit. Okay, so just a capacitor in an AC circuit. Now let's say you've got two circuits side by side. One is a DC supply. You've got a capacitor, you've got a lamp, and let's say you got a switch so that you can close the switch. And the other one is an AC supply. Let's say you got a lamp and a capacitor and a switch. So here's your lamp, your capacitor, and there's a switch. And the symbol for a capacitor in a circuit is the letter C. Okay, and this is an AC supply. Now, when you close the lamp in the DC circuit, when you close the switch so that the circuit is complete, what happens is that the current will flow, and as soon as the capacitor plates are fully charged, the current stops flowing. As long as the current flows, the lamp will glow, and then you know what happens when there's a capacitor in a DC circuit. The current will eventually come to a stop, so then the lamp will stop glowing. Okay? However, so the lamp stops glowing when the capacitor is fully charged, because charges never flow through the capacitor plates, they just accumulate on the sides, so that acts like a break in the circuit, okay, in a DC circuit. If you have an AC circuit and you've got a capacitor there, what happens is charges go back and forth. and the terminals keep switching from positive to negative. So the capacitor plates are alternatively charged and discharged. So the lamp continues to glow in an AC circuit. So a capacitor does not act as a brake in an AC circuit. Okay, so it acts differently in an AC as well as a DC circuit. So that's one. And the other thing is, just like how when you last in year 11 you learned about Ohm's law, and that was to do with when you had a resistor in a circuit, okay? And suppose if instead of a resistor you have a capacitor in an AC circuit, and let's say we get a variable rheostat there, variable resistor, and you're measuring the circuit current, and you have a capacitor in this circuit, and you want to measure the voltage across the capacitor plates for different currents. So the rheostat is there just to change the size of the current, and for different currents you're measuring the voltage across the capacitor plate, and the meter is there to measure the circuit current. It's just a series circuit. So if you draw a graph of voltage across the capacitor against circuit current, so current is measured in amps, voltage is measured in volts, you're going to get a straight line graph through the origin, which tells you that the voltage across the capacitor is directly proportional to the current. Okay, that means as voltage increases, current increases as well. So whenever you have a proportional relationship, you have the proportionality constant, and this proportionality constant is XC, which is the reactance of the capacitor. So the reactance of the capacitor is the current limiting effect of the capacitor. It does not mean that this heat energy is lost in the capacitor. It's not. The only place that converts electrical energy to heat energy is a resistor, but this is the reactance of the capacitor, okay, and that is measured in ohms like we saw earlier. So this is the connection between voltage across the capacitor plates, the current in the circuit, and that's the reactance, okay. Now, the other thing that we're looking at in this lesson is also what are the factors that affect the reactance of a capacitor. Now, its reactance has to do with the current limiting ability. So, higher the reactance, smaller the current, okay? So let's think of there are actually two things that affect the reactance of a capacitor. One of them, it's an AC circuit, is the frequency of AC, and the other one that affects the reactance of the capacitor is the capacitance itself. How much charge can it hold per volt? Okay, now let's take the frequency into account. So you've got reactance. Now, if the frequency is high, it means that the charges are moving back and forth really fast. If the charges are moving fast, that means the current is high. If the current is high, then the reactance is low. So that means the reactance is inversely proportional to frequency. Okay? Then the other thing is, if the capacitance is very large, that means the capacitor can store more charge. That means more charge will have to flow through the circuit. If more charge is flowing through the circuit, that means the current is high. If the current is high, then the reactance is low. That means reactance is also inversely proportional to the capacitance. So in other words, the reactance of a capacitor is inversely proportional to both the frequency and the capacitance, and the proportionality constant is 1 over 2 pi. So the reactance of the capacitor, the formula to calculate the reactance of a capacitor, one of them is this, the other one is 1 over 2 pi Fc. But the way that this is given in your formula sheet is capacitor reactance is 1 over omega c, because omega is angular frequency and omega is equal to 2 pi f. Okay, so that's how this is given. So on the formula sheet, you've got xc is 1 over omega c, and you've got next to it omega is 2 pi f. So you combine both these and you get that. So that's today's lesson for you. Bye for now, and I hope that made sense.